Welcome back to the deep dive. So you sent us this huge stack of sources.
Yeah, a really interesting pile. We've got articles, research papers, some pretty dense technical white papers.
And it's all about a topic that I think, a lot of people they shy away from it, computer architecture.
They hear the word architecture and immediately think it's just for engineers, that it's way over their heads.
Right, that it's too complex.
Yeah.
But our job here is to basically take all that raw information and really boil it down.
Exactly. Our mission today is to distill it into what you absolutely need to know to be, well, truly informed on this. We're moving past the surface level.
I mean, everyone sort of knows what a CPU is or what RAM does.
Sure, but that's like knowing what a brick is without understanding what a house is. We want to understand the big picture.
The blueprint.
The blueprint.
Yeah.
The plan that connects all those individual parts into something that actually works.
Yeah, because the sources really hammer this home. Without that foundational design, you could have the most powerful components in the world, and you just have a pile of junk.
A chaotic and useless outcome, I think one paper called it.
That's it. It's the difference between a pile of lumber and, a dream treehouse.
That is the perfect framing for it. That structure, that set of rules for how everything talks to each other, that's hardware architecture.
It's not just what's in the box, but how it all cooperates.
How it communicates, how it shares resources. It's the invisible framework that makes your phone, your laptop, your console actually run.
So that's our mission for this deep dive, to give you that core knowledge.
And we have to start with the single most important concept, the foundational blueprint for almost everything.
The von Neumann architecture.
The one and only. It's named after the mathematician John von Neumann, and its principles are so solid they still govern pretty much every general-purpose computer made today.
Okay, but why? Why has this one design lasted for, 80 years?
I think it comes down to its brilliant simplicity. Von Neumann basically laid out this universal recipe, a fundamental loop that never stops.
The fetch, decode, execute loop.
Fetch an instruction, decode what it means, execute the task, and then just repeat billions of times a second. And crucially, he decided that the instructions and the data they use should share the same memory space.
See, that sounds simple, but I can already hear the problem. If your instructions and your data are all using the same road,
You're going to get a traffic jam.
a massive traffic jam, right?
You're pointing directly at its biggest weakness, what engineers call the von Neumann bottleneck. And we'll definitely get into that. But the fact that it's still here is a testament to how simple and cheap it is to build, and how clever engineers have been at finding ways to work around that bottleneck for most everyday tasks. It really is the universal recipe book.
Okay, so we have the blueprint, the von Neumann design. Now let's start populating the city. If architecture is the city plan, we need to know what all the buildings do.
I love the component city analogy. It really works. And at the absolute center of this city, the mayor's office, the city hall, that's the CPU, the central processing unit.
The boss brain.
The boss brain. It does all the math, all the logic. It makes every single decision that the computer executes. It's in charge.
But when we talk about a modern CPU, it's not just one mayor in that office anymore, is it? We're talking about cores.
Right. It's like having a whole committee of mayors. In the old days, a CPU had a single core, so it could only really think about one thing at a time.
Sequentially.
Exactly. But today, your phone probably has 8 cores. Your laptop might have 16. Each one is a separate brain capable of running its own operation independently.
But the architecture has to be the thing that keeps them from tripping over each other, right? How do you stop all 16 mayors from trying to pass the same law at the same time?
That's where the genius of the architecture and the operating system comes in. They act as the city manager, dividing up the work. So if you're editing a video, one core handles the video playback, another handles the color correction, a third is working on the audio.
They're working in parallel.
It's massive parallelism. And you even have things called threads, which are like virtual assistants for each mayor, letting one core handle 2 tasks at once. It's this whole layered system of optimization.
Okay, so from the brain, let's go to the part that causes, I think, the most confusion for people. The difference between memory and storage.
This is non-negotiable. You have to get this distinction. They have completely different jobs in our city.
Let's start with the fast one.
RAM.
RAM, or random access memory, is the temporary high-speed workspace. It's like the giant whiteboard in the mayor's conference room.
Okay.
The data the CPU needs right now gets put on that whiteboard, but it's volatile. The second you turn the power off,
The board is wiped clean.
everything's gone. It's only for the meeting that's happening at this very moment.
And it's physically built for speed, which is key to the architecture.
Absolutely. It uses something called DRAM, which is fast. We're talking nanoseconds. But it's a trade-off. You can't make it super fast, super big, and super cheap. So it's the middle ground.
Okay, so that's the whiteboard. What's the permanent record? Well, you have two types. First, there's ROM, read-only memory. This is like a carved stone tablet in the city's foundation.
Can't be changed.
Exactly. It holds the computer's most basic startup instructions, the stuff it needs to know just to wake up.
And then there's the big word.
The warehouse, that's storage. Your hard drive or your SSD. This is the long-term archive for everything. Your operating system, your games, your photos. It's huge, it's non-volatile, but it's much, much slower to access than RAM.
Milliseconds instead of nanoseconds.
A huge difference. And the whole point of the architecture is to manage moving things from that slow warehouse into the fast conference room when the mayor needs them.
So we've got the mayor, the conference room, the stone tablet, and the warehouse. But they're all in different buildings. How do they talk to each other? That brings us to the system bus.
The superhighway. The
Yeah.
bus is the city's entire road system. It's a complex set of electrical wires that connects the CPU, the memory, and everything else.
And it's not just carrying stuff, right? The sources say it also carries the traffic signals?
That's a great way to put it. It carries the data itself, but it also carries the addresses where the data is going, and the control signals, which are like the traffic lights telling everyone when it's their turn to go.
Which means if the bus is too slow.
The whole city grinds to a halt. You can have the fastest mayor in the world, but if the roads are just a dirt path, nothing gets done. That's a classic bottleneck.
Before we dig deeper into the bus, two other quick players. First, cache memory.
Ah, cache. This is one of the most brilliant architectural tricks ever. It's a tiny, tiny layer of extremely fast memory that usually lives right on the CPU chip itself.
A speedy shortcut stash, as the source called it.
Perfect.
But wait, if it's so fast, why have RAM at all? Why not just have a ton of cache?
Money and physics. Cache is built from something called SRAM, which is blazing fast, but it's physically big and ridiculously expensive, so the architecture can only afford to have a few megabytes of it.
So it's like a little notepad the mayor keeps in his pocket for the most important numbers.
Exactly. The architecture tries to guess what the mayor will need next from the big whiteboard and copies it onto that little notepad. If the mayor finds it there, that's called a cache hit. It's a massive speed boost.
It's all about intelligent prediction.
All of it.
And finally, the link to us, the users. Input-output devices.
Your keyboard, your monitor, your mouse, they're the city's ambassadors to the outside world. The I/O architecture is all about managing those communications without distracting the mayor from his important internal meetings.
Okay, let's put it all together. The real-world example. Playing a video game. You fire up a huge open-world RPG. Walk us through the city.
Okay, the second you click load game, the city comes alive. The CPU, the mayor, sends an order to the I/O controller to get the game world data from the storage warehouse.
So a truck goes to the warehouse.
A very fast truck. That massive chunk of data travels along the system bus and gets loaded onto the big whiteboard, the RAM. At the same time, the game's instructions, the rules of the world, are also loaded into RAM.
And then the mayor's committee, the cores, gets to work.
That's right. One core might be running the game's physics. Another is handling the AI for all the characters in the town. Several more are working together to render the graphics you see on screen.
And they're all constantly grabbing data from RAM.
And putting the most used bits into their super fast cache notepads. Every single action, every sword swing, every pixel on the screen is data flying across that system bus. If any one of those parts can't keep up, the bus, the RAM, anything, you get lag. You get glitches.
So that smooth, seamless experience you have is basically a perfectly managed, high-speed city running without any traffic jams.
It's architectural harmony.
Okay, section 2. We've seen the city layout. Now we need to see the rhythm, the actual pulse of the machine, the instruction cycle loop.
Right, this is the mechanical breathing of the computer, the fetch, decode, execute cycle. This is what the CPU is doing constantly, billions of times every single second.
Let's break down those 4 steps because they're fundamental. Step 1, fetch.
Fetch is all about what's next. Inside the CPU, there's a little register called the program counter. Think of it as a bookmark. It holds the memory address of the very next instruction the CPU needs to run.
So the CPU looks at the bookmark.
It looks at the bookmark, puts that address onto the address bus, and basically yells to RAM, "Hey, give me what you've got at this location." The instruction at that address travels back along the data bus and gets loaded into another special spot in the CPU, the instruction register.
Okay, so the instruction has been retrieved. It's sitting in the register. Now what?
Now we decode. The instruction is just a string of ones and zeros. The CPU's control unit has to look at that string and figure out what it actually means. It's like a translator. It sees the binary code and says, ah, this is an ADD command.
And it prepares the right internal circuits for that command.
Exactly. It gets the right part of the CPU, the arithmetic logic unit, ready to do some math.
Which leads us right into the action phase. Execute.
This is where the work gets done. If the instruction was ADD, the two numbers are added. If it was a command to move data, the data gets moved. This is the whole point of the cycle.
And the final, often forgotten step, store.
Right, you have to do something with the result. Sometimes the answer is just needed for the very next step, so it stays inside a CP register. Other times, it's a final result that needs to be written back out to RAM for later use.
And once that's done,
the program counter, our bookmark, moves to the next line in the recipe, and the whole cycle starts over again. Fetch, decode, execute, store. Relentlessly.
Let's trace that on a more concrete example, that data's wild ride. Let's follow a single piece of data when you open a photo.
Okay, so you double-click the photo icon. Your mouse click is an input signal. The I/O controller tells the CPU, hey, user did something. The CPU fetches the instruction for open file.
Now it needs the actual photo data, which is in the slow warehouse.
Exactly. So the CPU sends a request. It puts the specific address of that photo file on the address bus, the map, so the storage drive knows exactly where to look.
And the data itself comes back on a different road.
The raw photo data travels back on the data bus and gets loaded into RAM. Now the CPU can process it, maybe resize it or apply a filter. Then it sends the final pixel data, again via the bus system, to your graphics card to display on the screen. The data is just constantly in motion, all directed by this cycle.
To really get this, we have to look closer at the buses in detail. It's not one big highway, is it? It's a team of specialists.
A tripartite system. You have to have them separate to avoid absolute chaos.
Let's start with the one carrying the actual stuff. Yeah. The data bus.
The data bus is just for the information itself, the photo, the numbers, the code, and the most important thing about it architecturally is its width.
How many lanes the highway has?
Perfect analogy. A 64-bit wide data bus means it has 64 parallel lanes. It can move 64 bits of data in a single tick of the clock. A 32-bit bus can only move 32. So you double the width, you basically double your data throughput.
So more lanes, less traffic. Makes sense. While that's carrying the cargo, the address bus is the GPS.
Yep. The address bus only carries addresses, binary numbers that point to a specific slot in RAM or a specific I/O device. It's just for location information.
And its width is also incredibly important, but for a different reason.
A critical reason. The width of the address bus determines the maximum amount of RAM your computer can even see. A 32-bit address bus can only generate about 4 billion unique addresses.
Which is 4 gigabytes of RAM.
And that's the hard limit. The whole move to 64-bit computing was fundamentally about widening that address bus so we could access terabytes of memory.
Okay, so data has its road, addresses have theirs. What keeps them in sync? The control bus.
The traffic cop. The control bus carries all the command and timing signals. So when the CPU puts an address on the address bus, it sends a signal on the control bus that says, read from this location or write to this location.
It's giving the orders.
It's giving the orders. It also handles things like, hey, I'm a device and I need to use the bus now. Or, I'm the keyboard and I have an urgent message. It's the arbitration system that stops everyone from talking at once. Without it, you just have electrical noise and corrupted data.
All right, Section 3. We're getting into the nitty-gritty of performance, the constant balancing act between speed and physical size. It all starts with the heartbeat of the machine. CPU cycles.
Yeah, every single thing a computer does is timed to a little crystal oscillator on the motherboard. It ticks, and that tick is a CPU cycle.
And the speed of those ticks is measured in gigahertz.
Billions of ticks per second. It's a staggering number.
But one tick doesn't equal one task, does it?
Not usually, no. Each tick just lets the CPU move one tiny step forward. A really simple instruction, like adding 2 numbers already in registers, might happen in one cycle.
Yeah.
But the full fetch, decode, execute process for a more complex instruction can take 4, 5, maybe more cycles to complete.
So the game for architects is to both increase the number of ticks per second, the gigahertz, and also to make the CPU do more useful work with each tick.
That's the whole game. But for a long time, the industry was just focused on one thing, cranking up the gigahertz, just make the clock tick faster. That's called frequency scaling.
And that hit a wall, a very hot
A
wall.
very hot wall. I'm sure you remember trying to overclock your first PC.
Oh yeah, you push the clock speed up, you see the performance jump, and then your computer just shuts down.
Or melts. The architecture has to protect itself. When a chip gets too hot, it engages thermal throttling, automatically slowing itself down to avoid damage. Plus, you run into that bottleneck problem again. If your CPU is ticking at 5 gigahertz, but your RAM can only feed it data at a 2 gigahertz pace, the CPU is just sitting there, idle, waiting for work most of the time.
So just going faster wasn't the answer. The architects had to get smarter. They had to become efficiency wizards. Which brings us to pipelining and parallelism.
These are the two techniques that define modern performance. Let's start with pipelining. It's just genius.
Okay, explain it.
Instead of doing the 4 instruction steps, fetch, decode, execute, store one after the other, like a single worker doing one whole job at a time.
You turn it into an assembly line.
You turn it into an assembly line. While one instruction is in the execute stage, the next instruction is already in the decode stage, and the one after that is being fetched.
So you have multiple instructions all moving through the pipeline at the same time.
At any given moment, every part of the CPU is busy working on a different piece of a different instruction. It dramatically increases the throughput, the number of jobs finished per hour, even if each individual job still takes the same amount of time to get through the line.
But that sounds risky. What if the result of the front instruction is needed for the second one?
That's the great challenge. It's called a pipeline hazard. Or what if there's an IF statement? The pipeline has to guess which path the code will take. If it guesses wrong,
You have to throw out all the work in progress.
flush the whole pipeline and start over. It's a waste of cycles. Modern CPUs have incredibly sophisticated branch prediction units just to minimize those wrong guesses.
So pipelining makes one assembly line super efficient. Parallel processing just build more assembly lines.
That's it. That's what multi-core processors are. It's the main reason our computers have gotten faster over the last 2 decades. If you have a task that can be broken into pieces, like editing a photo,
You can have one core working on the sharpening, another on the color balance.
and they're doing it truly simultaneously, it's the only way to handle the dozens of things your computer is doing right now, even as we're just talking.
Okay, that covers processing speed. Now, data access speed. The memory hierarchy. Why? The layers. We touched on this, but why not just build one giant super fast memory?
It's the most important question, and the answer is always cost and physics. You simply cannot build something that is huge, super fast, and cheap. It's not possible. So you compromise by creating layers.
Let's run through them again, focusing on the trade-offs. At the top, the fastest and smallest.
Cache. The L1, L2, and L3 caches. Tiny, expensive, and physically right next to the CPU cores. The CPU's pocket notebook. A cache hit means no waiting.
Then the middle layer.
RAM, the big whiteboard. Much bigger, much cheaper per gigabyte, but also a bit slower and farther away. Data moves from RAM up into cache only when the system thinks the CPU is about to ask for it.
And at the very bottom,
The warehouse.
Yeah.
Storage. Your SSD. Massive capacity, cheapest per gigabyte, but orders of magnitude slower to access. The whole principle of the hierarchy is to make sure the data you need right now spends as much time as possible at the top in the fastest layers.
it's an elaborate guessing game.
It's an incredibly intelligent and complex guessing game, and when it works well, you never even notice it. You only notice when it fails and you have to wait for something to load from the warehouse. That's a failure of the hierarchy.
Okay, so far we've mostly lived in the world of von Neumann, but that's not the only blueprint out there. This brings us to the battle of the blueprints, von Neumann versus Harvard.
Right. This is a really fundamental fork in the road of design. We know von Neumann. One memory, one bus for both instructions and data. The big kitchen analogy. Simple, versatile.
And prone to traffic jams, the bottleneck.
Exactly. The Harvard architecture was designed specifically to solve that one problem. It creates 2 completely separate systems.
2 kitchens.
2 kitchens. It has a separate memory and a separate bus just for instructions, and a different separate memory and bus just for data.
That sounds way faster. Why isn't everything built that way?
Because it's more complex, it uses more hardware, it's more expensive, and it's harder to program for. But for tasks where you need to be fetching instructions and processing data at the absolute maximum non-stop rate.
Like a dedicated signal processor for audio.
Perfect example. Digital signal processors or high-performance microcontrollers in cars or planes. They can't afford a single hiccup from a bottleneck. So for them, the speed of the Harvard design is worth the extra cost and complexity.
So your laptop is probably a von Neumann machine, but parts of it, like the chip that handles your sound, might be using Harvard principles internally.
It's a hybrid world. Architects steal the best ideas from everywhere.
Next up, the actual language the CPU understands. The instruction set, RISC versus CISC.
This is a huge one. This is basically the story of the modern smartphone. So the instruction set is the list of commands the CPU knows. For decades, the dominant philosophy was CISC, complex instruction set computing.
Intel's by 86. The big one.
The heavyweight champ. The idea behind CISC was to make the instructions powerful. One single CISC instruction might do three things at once: load data from memory, do a math operation, and store the result.
Fancy complex recipes. That sounds efficient.
On the surface. But those complex instructions are a pain to execute quickly and efficiently inside the chip. They're hard to pipeline. Funnily enough, modern CISC processors actually break those complex instructions down into simpler RISC-like steps internally before they run them.
Which brings us to RISC, reduced instruction set computing.
The challenger. Popularized by architectures like ARM. The philosophy here is the opposite. Keep it simple. Every RISC instruction does just one tiny thing: load, store, add.
Short, simple recipes.
That's it. And because they're so simple, they can be executed incredibly fast, usually in a single clock cycle. They pipeline beautifully. And the most important part, the chips are simpler, smaller, and use way, way less power.
And that's why every single smartphone uses an ARM-based RISC processor.
Bingo. For a mobile device, battery life and low heat are more important than the absolute raw power a big CISC chip might have. It's architecture driven by the specific needs of the device.
Okay, finally, how does this pristine internal city talk to the messy outside world I/O architecture?
This is the Customs and Immigration Department. It manages everything coming in or going out. Devices connect through physical ports like USB or HDMI, and those ports are managed by controllers, which are like the traffic cops for each specific device.
So if I press a key on my keyboard, how does that message get to the CPU without constantly bothering it?
There are two main methods. The first is interrupt-driven I/O. This is the polite way. When you press a key, the keyboard controller sends a special signal on the control bus called an interrupt.
It's like a polite knock on the mayor's door.
Perfect. The CPU stops what it's doing for a microsecond, handles the key press, and then goes right back to its original task. It's super efficient because the CPU isn't wasting time constantly asking the keyboard, "Did you press anything yet? How about now?"
But that polite knocking wouldn't work if you're downloading a huge file, right? The hard drive would be knocking a million times a second.
The CPU would get nothing done. It would be paralyzed. That's why for big, bulky data transfers, we use the second method, DMA, or direct memory access.
It bypasses the CPU.
It completely bypasses the CPU. There's a special little helper chip called the DMA controller. The CPU basically tells it, "Hey, you, take this huge file from the network card and move it directly into RAM. Let me know when you're done."
So the mayor delegates the big, boring job.
Exactly. The DMA controller takes over the buses and manages the entire transfer, freeing up the CPU to keep running your programs. This is how you can download a game in the background while still using your computer without it slowing to a crawl. It's all part of the blueprint.
We've covered a lot of ground, from a single CPU cycle to these massive parallel systems. As we wrap up, it feels important to look at the bigger picture here. The evolutionary journey of architecture is just staggering.
It really is. I mean, you look at something like ENIAC from the 1940s, it filled a room with vacuum tubes, and it had less computing power than the little chip in your musical greeting card.
And it was just the most basic version of this von Neumann blueprint we've been talking about.
The absolute barest bones, every single innovation since, the transistor, the integrated circuit, pipelining, multi-core, it's all been about making that same fundamental process faster, smaller, and more power efficient.
But we're hitting physical limits with silicon. So where do architects look next?
Well, they're looking somewhere completely different, to a new kind of physics. The next step is probably quantum architectures.
Which just breaks everything we've talked about.
It shatters the whole model. Our entire discussion is based on the bit of value that is either a 0 or a 1. A quantum computer uses equip-it.
Which can be a 0, a 1, or both at the same time.
Exactly, superposition. The whole fetch, decode, execute loop becomes meaningless because a quantum computer isn't processing things sequentially. It's exploring all possibilities simultaneously. Quantum architects are designing with concepts like entanglement and interference. It's a complete reboot of what architecture even means.
Which leads to the people who do this work. This isn't just an abstract topic, it's a career. The human element.
For sure. If you've been listening to this and you're fascinated by these trade-offs, speed versus heat, RISC versus CISC, how to design a better cache, then you have the mind of a computer architect.
They're the ones drawing the blueprints for the next generation of machines.
They're solving the big problems, like how do we make data centers more energy efficient? How do we build a chip that's optimized for artificial intelligence?
And they work with the hardware engineers.
The people who take that beautiful blueprint and figure out how to actually build it in silicon, how to lay out billions of transistors without them melting, it's an incredible partnership between the logical and the physical.
And the sources mentioned the need for diversity here. That new ideas come from new perspectives.
Absolutely. You can't solve the next generation of problems using last generation's thinking. Bringing in people with different backgrounds, different ways of looking at a problem, that's how you get real innovation. You avoid getting stuck in an architectural rut.
So to bring this all home for you, the listener, we want to challenge you. Fostering creativity. Be an architect for a minute. Redesign the blueprint.
Yeah, break the rules we just spent an hour explaining. For example, what if the system bus was just gone? What if all the components talk to each other wirelessly with localized high-speed signals?
You'd kill the bus bottleneck, but you'd create a whole new nightmare of signal interference and power management.
Exactly. Or think about the CPU's job. It's all logic and math. What if you added new specialized cores, not just general purpose ones? What if you designed an art core or an emotion core?
What would that even do? How would you design a circuit that processes something subjective, not just numerical?
That's the question. It forces you to think beyond the blueprint we've inherited from the 1940s and imagine what else computation could be.
So we started this deep dive with a pile of parts and a complex topic. But I think we've ended up with a real understanding of that blueprint, the architecture that acts as the essential glue.
You now know the rhythm of the machine, that fetch, decode, execute loop. You understand the trade-offs in the memory hierarchy and why we have these different architectural styles, like von Neumann and Harvard.
It's the foundation. And understanding that foundation sets us up perfectly for our next deep dive.
Because once the hardware is built according to the blueprint, you need a manager to come in and actually run the city.
Exactly. Next time, we boot up the operating system, the software box that takes this physical architecture and uses it to run your apps and make the whole thing useful.
But before we go, let's leave you with one final thought, something to mull over. We've talked a lot about the push for speed pipelining, parallelism, trillions of instructions per second.
And how good architecture has to balance that speed with safety, with things like thermal control.
Right. So my question is this. If future architectures, maybe quantum, make speed and power virtually limitless, what becomes the architect's main job then? What's the new bottleneck?
If you don't have to worry about physical limits anymore, what do you worry about?
I think you have to worry about control and fairness. If we build these boss brains that operate at speeds we can't even comprehend, what architectural safeguards need to be built in from the very beginning to make sure they operate safely and for everyone's benefit?
The problem shifts from making it fast enough to managing something that might be uncontrollably powerful.
It's no longer about the chip thinking too quickly and getting too hot in a thermal sense, but maybe in a societal one.
Something profound to think about. Thank you for joining us on the Deep Dive.